Good day, everybody, and welcome to this online presentation. My name is Meli, and it is a privilege to be here and present this work. I'm a lecturer at the Zurich University of Applied Sciences in Winterthur, Switzerland. I also lead a research group at the same university where we work on low-power embedded systems and energy harvesting, often in combination with wireless systems. In this talk, I will cover the motivation, the issues or difficulties related to the work, the main elements of the node. I will discuss the measurements and results, then I will conclude. I would like to acknowledge the support of our institute in an internal project and the support of the Horizon 2020 program for the Amende project with contribution from several partners. What is the motivation for this work? Several millions of IoT nodes are expected. Many of them must be energy autonomous. But how should those nodes be powered? Mains are reliable, but mobility suffers. Batteries need to be replaced when they fail or are used. There are sometimes serious ecological issues associated with them. Energy harvesting is considered as an alternative, but what about cost? The ability to deliver sufficient energy, the need for special components and know-how. Solar cells have been used in several cases. Here are some examples from our own group. The Bluetooth Smart day and night node with a small solar cell. The low-cost wireless beacon node that uses LEDs as low-cost harvesters. The LoRa node powered with a relatively large dye-size solar cell. As far as we can tell, not much has been done in low light conditions, even less combining long-range communication systems and low light. The purpose of this work is to use a long-range wireless system and to work well below 100 lux in a building where LoRaWAN with spreading factor 7 is good enough for the range. Let's look at one or two issues faced for such a task. Long-range systems such as LoRa, Sigfox, Narrowband IoT require 100 to 10,000 times more energy than, say, short-range systems such as Bluetooth Smart. We are talking here about several millijoules to hundreds of millijoules, depending on the range and the payload. And you will need to harvest that energy at a rate that is good enough for the application, not easy in low light conditions. The peak currents are also higher for long-range systems. It means that special care is needed for the power management electronics and the storage. To achieve our goal, we combine power-efficient components and efficient energy harvesting. Which elements are used in the node? The solar cell from Lightricity is 8 quadrat centimeter. It can work in low light conditions and delivers a voltage that is high enough, so there's no need for a booster. It delivers up to 22 microwatt per quadrat centimeter at 200 lux. At 20 lux, one will harvest about 8.5 millijoules in 10 minutes, assuming a transfer efficiency of 80%. The power management is from EM Microelectronic. It is not made for high currents and therefore requires an external converter. It uses a short-term and long-term strategy to allow fast reaction and accept different storage types. We use it in a single storage mode with a 10 millifarad supercapacitor. Other elements are the low-power Apollo 2, a Cortex M4 compatible microcontroller from Ambic Micro, the LoRa SX1276 transceiver from Semtech, the BME 680 from Bosch that measures temperature, relative humidity, air pressure. The system also integrates a serial FRAM from Fujitsu for low-power, high-endurance, non-volatile storage. That helps in the low-power harvesting strategy. Instead of keeping the system powered and in a deep sleep mode that might require several microamps, we totally switch the load off after saving the important data in the FRAM. The timer in the power management is used to switch the load on or off after a program time, here 10 minutes. The load is powered on only when there is enough energy in the storage to do the work. Appropriate data saved before in the FRAM is first read to allow the work to continue. In this way, the system harvests and uses the energy with a maximal efficiency. To test the low-light performance, the following setup was made. The node was placed in an office with the possibility to use artificial light or natural light coming through windows and curtains. Transmission power was about 8 dBm in SF7. Illuminance was recorded. A power analyzer was set up to record the supercapacitor and solar cell voltages. The frames transmitted were captured by LoRa gateways and the result processed and displayed. The measurements shown were made in an afternoon in July. There are 4 illuminance zones for the test. A first zone with more than 100 lux of artificial light. A second zone with light from windows only, varying between 30 and 10 lux for about 3 hours. A third zone when artificial light was switched on again. A fourth zone well below 20 lux from natural light. This figure shows activities on the node side. Up in green color, we see the 4 illuminance zone. Below are voltage activities. The upper trace is the solar cell voltage. The changes on the envelope are related to internal activities of the power management, such as measurements of the input energy and protection of the storage. The lower trace is the storage voltage. In zone 1, where we have more than 100 lux, the supercapacitor is charged, and when a program limit is reached, the embedded system makes measurements and transmits the data, point A and B. The storage is then short-circuited to empty it and to simulate a cold start. With more than 100 lux, recharging is fast and the system is soon able to measure and to transmit again. That's what we have with points C, D, and E. Then we enter zone 2 with less than 30 lux. The activities continue and the voltage of the storage stays nearly constant. The system is sustained. The energy that is harvested is sufficient to keep the voltage, to keep the system going. Then we short circuit the storage again and we discharge it. And it takes longer now to recharge the storage and to reach the point where we can start transmitting again. We are here below 30 lux, so it will take more time. As soon as we reach that point, measurements are made and data is transmitted again. But here, because we are quite low in terms of illuminance, the system is no longer sustained and the voltage of the storage starts dropping down. Then we enter zone 3, the lights are switched on, the system will recover, and we start sending again in a sustained way. Then we enter zone 4, and here we are well below 20 lux. The system still sends some data, but the voltage of the storage is decreasing until the system completely stops. The LoRa frames that are sent are captured, decoded, and the results can be seen on this slide. 2 energy parameters measured in a coarse way by the power management. The input current that mirrors the illuminance, we can clearly see the high and low illuminance points, and the storage voltage. The form also resembles that of the log from the power analyzer. The sensor parameters are the temperature, relative humidity, and air pressure from the BME 680. The application clearly does its job. In conclusion, we designed and demonstrated a long-range energy autonomous node powered by a small solar cell and capable of working at 30 lux, convenient for a building automation application. By increasing the measurement interval, it is possible to achieve a better range. Future works will seek to improve the performances of the system. Thank you for your attention.